Now we move on to damped free vibration. When we have free vibration with damping, we're going to have an equation of motion that has an x double dot term, an x dot term, and an x term. So we do have, unlike before with undamped vibration where there was no x dot term, now we have this cx dot. And we're still talking about free vibration, so our right-hand side is still 0. So this is generally what our equation of motion is going to look like when we have free vibration with damping, and we'll again be given some initial conditions, an initial value for the position and initial value for the velocity. First, we can find the natural frequency of our system. And anytime we have a 1 degree of freedom system, we're going to want to find the natural frequency, and it's always going to be found by taking the square root of the equivalent spring constant divided by the equivalent mass. So damped or undamped, the natural frequency is going to have the exact same calculation. Now, we can find some additional parameters when we have damping that didn't make sense when we had undamped systems. So we're going to be interested in finding the damping ratio, zeta. We're going to find that by taking the equivalent damping coefficient divided by 2 times the equivalent mass times the natural frequency that we just found. And we'll talk about what the damping ratio will tell us on the following slide. So we can take the natural frequency, we can take this damping ratio by their definitions, and we're able to rewrite our equation of motion in this form. So we can divide through by that m, and we can rewrite the equation of motion x double dot plus 2 zeta omega n x dot plus omega n squared x equals 0. So we haven't changed anything, but we're expressing it in terms of our natural frequency and the damping ratio. With our system rewritten, again, we'll still be given our initial conditions here, but if we're interested in solving our system, we have this second order ODE, so we can solve it once again like we did for the undamped systems by creating the characteristic equation. Right, so the x double dot will go to a lambda squared. We now have an x dot term that goes to lambda, and then the x just goes to 1, and that's equal to 0. So the characteristic equation, we want to find the lambdas that are going to make this expression true. We want the roots of the characteristic equation. So for any damped system, this is going to be the solution to our characteristic equation. These are the roots of lambda. If we remember back to system dynamics when we were working with transfer functions, these were the poles of our transfer function when we had a second order system. And our interpretation of what the values of those poles were, or what the values of the roots of the characteristic equation are going to be the same. Depending on the values of lambda, which are going to depend on the value of zeta really, we can make some inferences about the type of behavior that our solution is going to have, the type of behavior that x of t will have. So in the event where our zeta value, that damping ratio, is between 0 and 1, that's going to mean that our lambda value is going to have a real part and an imaginary part. So a real part of this negative zeta omega n plus or minus j times the damped frequency omega d. And when we have a zeta between 0 and 1, which is to say that the roots of the characteristic equation are complex with a non-zero real part and a non-zero imaginary part, we are going to have an underdamped system. And therefore our x of t solution is going to have a certain look about it that we'll get to what the solutions look like for all of these types of systems on the next slides. In the event that we have a zeta value greater than 1, that is going to mean that our lambda values, the roots of this characteristic equation, are going to be purely real. They're going to be real but unique. And this is going to mean that we have an overdamped system. We can have the event where our zeta value is equal to 1, which is going to give us lambda values that are real but repeating of negative zeta omega n and negative zeta omega n. In this event with real but repeating roots, we're going to have a critically damped system. If we have a zeta value equal to 0, the real part of the characteristic equation's roots is going to be 0, so it's going to be purely imaginary. It will just be plus or minus j omega n. And this gives us an undamped system. And this is exactly what we saw in the previous subsection. We had purely imaginary roots that were complex conjugates of each other, and we saw how to solve those undamped systems. So if this is our zeta value, we already know how to handle this from the previous subsection. And the final possibility, our zeta value could be negative, less than 0, in which case we have an unstable system where instead of energy being dissipated as time goes on, energy is actually being absorbed. We're not going to see any systems like this in the mechanical systems that we study, but potentially these unstable systems do exist in thermal systems, electrical systems, etc. So it is important to know what to do if zeta is less than 0, but we're not going to be covering it in this course. We're only going to be looking at stable systems. So those that are going to reach some steady state value given enough time, or in the case of the undamped system, where we have neutral stability, our value is going to keep oscillating between some finite max and some finite min. In an unstable system, as time goes forward, the behavior of our system is going to go towards positive infinity or negative infinity.